So we start a new topic today, stability and compensation of amplifiers. We briefly discussed this earlier, but now we'll formalize it and then talk about compensation. Before we begin, there was a mistake I made in slide 20, where I was comparing these two polynomials, the one which had the constant term unity and the other where the coefficient of the s squared term was 1, and had said that in the equation of the second type, whatever I had said, the correct thing is the coefficient of the s raised to n minus 1 term will be, Pn will be Pn, the highest of the pole frequencies. I had said last time that it was the s term, not the s raised to n minus term. So please make this correction. Okay, so we review feedback theory in one slide and then go talk about formalizing stability. So this is from lectures 5 and 6, primarily from 5. We had discussed at that time that for a negative feedback loop, the transfer function can be written in this form, a over 1 plus a beta. And then we had said that if at some frequency omega naught, the a beta becomes equal to minus 1, so that the denominator becomes 0, then the amplifier will show sinusoidal oscillations independent of the input. This is good while we are designing an oscillator, but this is not good if we are using the system as an amplifier. So, and now our discussion will be for amplifiers. So with this background, let us quantify and formalize this issue of stability and oscillations. I may have said this before, the feedback factor beta can vary between 0 and 1. 0 refers of course to no feedback, that is an open loop system. 1 implies a unity gain feedback, and beta is never made greater than 1 because greater than 1 means the closed loop gain is less than 1, which is never really of interest. The worst case situation from a stability perspective occurs when beta is equal to 1. And so we will discuss henceforth, we'll assume that beta is 1 in our discussions, and whatever results we arrive at will be valid for beta less than 1 also. So we say that for beta equal to 1, if at some frequency omega naught a j omega naught is minus 1, then the amplifier will oscillate. Now we can write this by saying that for this condition to be satisfied, the magnitude of this complex number must be 1 and the phase of this complex number must be 180 degrees or minus 180 degrees, same thing, but minus is more physical, as we'll see in a minute. So we say that oscillations occur if when the magnitude of the gain becomes 1 at that frequency if the phase is minus 180 degrees. Okay. So now to study stability and non-oscillating systems, we need to study the phase behavior of a j omega as kind of introduced here. So let us spend a few minutes discussing the phase and plotting the Bode phase plot of amplifier transfer functions. Before we begin, I want to define a term called phase margin. This will be critical in our stability analysis. Often it is just called PM for phase margin here. The phase margin for any transfer function a j omega is defined as 180 degrees plus phi 0, where phi 0 is the phase of the transfer function when the gain becomes 1, the phase of the transfer function when the gain becomes 1 minus the phase of the transfer function at midband frequencies. Alright, midband is that region where frequency was not having an effect on the gain. We have seen the midband gain before. The midband gain, of course, is either, it's a scalar, so it is either a positive number or a negative number. So the phase of the midband gain is either 0 degrees or 180 degrees. If the overall gain is negative, it will be 180 degrees or minus whatever. For our purposes, we'll assume this phase to be 0 just to simplify the numbers. But the definition of the phase margin is this 180 degrees plus phi 0. So for us, this number is 0, and therefore the phase margin is 180 degrees plus the phase of the transfer function at unity gain frequency when the gain becomes 1. Okay, so now let us study the phase of this transfer function. So we'll start with the simplest transfer function, a single pole. Let us see how the phase of this varies with frequency. So we take 3 cases as we did for the gain. We have studied this for the gain as a function of frequency. Now we'll study the phase. So we say for if omega is much less than omega 0, for such frequencies, this term is very small and it can be ignored, and therefore this is just a constant, and so the phase of this transfer function at very small frequencies is 0. When the frequency is equal to omega 0, the pole frequency, then this cancels and we get A equal to A0 by 1 plus J. So the phase of this is, of course, how much is the phase? The phase of the denominator is tan inverse 1, which is 45 degrees, but it's in the denominator, so in the numerator it will become minus 45 degrees. And for omega much greater than omega naught, when we can ignore the 1, then we can write it as A naught omega naught by J omega, and so the phase of this is minus 90 degrees. At 0.1 omega naught, if omega is 0.1 omega naught, you can calculate the phase turns out to be minus 5.7 degrees, and at omega equal to 10 times omega naught, the phase turns out to be minus 84 degrees. Also note that theoretically the phase becomes 90 degrees. So the phase of this is actually this one. It is tan inverse omega by omega naught. That is the phase in fact. So tan inverse of omega by omega naught becomes equal to 90 degrees only when omega is infinite, because tan of 90 degrees is infinity, tan inverse of infinity is 90 degrees. So theoretically the phase of this transfer function becomes minus 90 degrees only as omega tends to infinity. At any finite value of omega, the phase will be very close to 90 but will not become exactly 90. Okay, with this let us do a Bode plot. Bode plot, as you remember, is a piecewise linear plot. It's an approximate plot. So as we saw, the phase is all negative. So we plot the phase on the y-axis negative, on the x-axis the frequency. And we saw that at omega equal to omega naught, the phase is minus 45 degrees. For omega much less than omega naught, it is 0. For omega much greater than omega naught, it is minus 90 degrees. So this is our Bode phase plot for a single pole transfer function. And because it's a piecewise linear plot, we are making it straight, although actually the phase here is about minus 6 degrees and the phase here is about minus 84 degrees. Again, emphasized again that at omega equal to omega 0, the phase is minus 45 degrees. Okay, let's look at a two-pole transfer function. So we have two poles. We will not plot this, you can plot this yourself. What I want to point out are a couple of characteristics of this transfer function. So as we just saw, the phase of one such term becomes minus 90 degrees only as omega tends to infinity. And if you have two terms, each term will contribute minus 90 degrees of phase. So the total phase at very high frequencies will be close to minus 180 degrees, but it will actually become minus 180 degrees only at omega, as omega becomes infinite. Now recall that for oscillations to occur, the phase must be minus 180 degrees at some frequency omega naught, at some finite frequency omega naught. What that means is that a two-pole transfer function, because it can never have a phase of minus 180 degrees at a finite frequency, only at infinite frequency, a two-pole transfer function will never achieve this condition. In theory, it will never achieve this condition, because this condition is achieved only for omega equal to infinity. And because this is never achieved, a two-pole transfer function, when put in negative feedback, will never ever oscillate, because this condition can never be satisfied. Such a system is called as unconditionally stable. So incidentally, instability means a system oscillates. It under negative feedback, when it oscillates, one says that it's an unstable system. So two-pole system is unconditionally stable. It never oscillates. In other words, in terms of phase margin, we'll keep referring to phase margin. The phase margin of a two-pole system is always positive, right? Because the phase margin is the actual phase, this phase, plus 180 degrees. And this is always not quite minus 180 degrees. It may be minus 179 or minus 135. So plus 180 is always positive. This is another way of saying actually that a system is stable, as we'll see. Okay, let's look at a three-pole transfer function. So this is a three-pole, and I have put numbers and I have kind of deliberately designed this transfer function so that it satisfies this condition. It satisfies the condition that at some frequency f0, which is not of relevance to us, but at some frequency this achieves a condition of minus 1, and so this will oscillate. So let's look at the Bode plot of this, and then we'll discuss this a little more. So 123 again is about 42 dB. It has three poles. So let us draw the Bode plot. So this is the Bode plot. So the black line is the Bode magnitude plot. The orange, pink, whatever this color is the Bode phase plot. Now let's look at this for a little bit. So the so the frequencies are multiplied by 10 raised to 7. So this is 10 raised to 7. This is 0.1 times 10 raised to 7. So 10 raised to 6. This is 10 raised to 8, 10 raised to 9, and something in between. The low frequency gain is 42 dB. So let's look at a magnitude plot first. So up to 10 raised to 7, which corresponds to 1, the gain is horizontal. Then it starts decreasing at 20 dB per decade. Then at 10 raised to 8, the second pole occurs. So the gain starts falling at 40 dB per decade. Then at 100, the third pole occurs, and the gain falls at minus 60 dB per decade. So this is the magnitude plot. Let's look at the phase plot. So for very low frequencies, 10 times less than the first pole, the phase of this transfer function is 0. At the first pole, 10 raised to 7, the phase is minus 45 degrees. So we start 1 decade below 10 raised to 7. So at 10 raised to 6, the phase starts falling and becomes minus 45 degrees at this pole frequency. Okay, now at this 10 raised to 8, which is 10 times higher than this term will contribute 90 degrees of phase. This term at f equal to 10 raised to 8, this is 1 plus j. So this will give a 45 degrees, minus 45 degrees. So minus 90 from here, minus 45 from here. The total phase at 10 raised to 8 is minus 135 degrees. So at 10, this is minus 135 degrees. So in one decade, this phase has gone by 90 degrees. Alright, in the first decade, it went by 45. In the second, by 90, because two poles are contributing to this part of the phase plot. Okay, the next data point is, we'll come back to this 33 afterwards, is the next pole is 10 raised to 9, one decade further. At 10 raised to 9, this pole contributes 90 degrees, this pole contributes 90 degrees, and at 10 raised to 9, this pole contributes 45 degrees. So 90, 90, 180, 45, 225. Negative, all negative. So at 100, the total phase is minus 225 degrees. Alright. And then, now for the next decade, these two poles have finished being their maximum phase contribution. This pole goes 45 degrees further. So over the next decade, this goes from minus 225 to minus 270. And then the phase remains constant at minus 270 degrees at very high frequencies. So this is how phase plots are plotted. Now, so if you look at the magnitude function, this is 0 dB, which is unity gain. So if you calculate, this is not an easy calculation actually, but if you do, you will find that at 33 times 10 raised to 7, the gain becomes unity. Alright, so the unity gain frequency is 3.3 times 10 raised to 8. And as I said, I have designed this deliberately so that at the unity gain frequency, the phase is exactly minus 180 degrees. So we know that this system will oscillate. Alright, so therefore the phase margin of this is 0 because the phase is minus 180 degrees. Plus 180 gives phase margin of 0. Alright, now let's look at this from let's do a bit of mathematics here with this transfer function. By the way, this is 123.21. I am writing this, it's actually 123.21. I am writing this just for its simplicity. It's assumed that it is 123.21 throughout. Okay. Now let's write that closed loop transfer function, a over 1 plus a. This is the whole thing is a over 1 plus a. Then we multiply out by this whole denominator, so it comes up here, so 123 by this plus 123. And if we expand this out, this is a cubic, there are 3 s terms, it will turn out to be this, s cubed. We expand this out and multiply by the coefficient of the s cubed term, which is 10 raised to 24. 7, 8, 9 is 24. So we multiply this thing out by 10 raised to 24. So we'll get s cubed plus 1.11 10 raised to 9, 1.11 10 raised to 17, 123 times 10 raised to 24, which also goes up. So this is our closed loop transfer function. Alright, now this is a cubic. I wanted to find the roots of this cubic. So I went to a website. The website is here at the bottom because finding roots of cubic, maybe your calculator can do, my calculator doesn't. Anyway, so I found the roots. So the roots are, there are 3 roots. One is a real root and the other 2 are complex roots. And in fact, they turn out to be only imaginary numbers, which is significant but not surprising, as you'll see in a minute. So so with these roots, because these are imaginary, we can write the transfer function as s plus this root, and this one will square so that the j goes away. So the square of this. So we'll get s squared plus 1.11 times 10 raised to 17. Now this is an interesting factorization, which actually is true only because these are purely imaginary roots. But it's interesting. So you see, this is 1.11 times 10 raised to 9. This is 1.11 times 10 raised to 9. So you compare it with this 1.11 times 10 raised to 9. So actually, the first root is nothing but the coefficient of s squared. And this, the s squared plus something, that something is actually the coefficient of the s term. So this is an interesting factorization which happens when, for a cubic, when two of the roots are purely imaginary, and they are, of course, they are conjugates as they have to be. Okay, so this is our transfer function factorized. Now you recall we had done in lecture 6 when we discussed negative feedback and positive feedback, and we are looking at the transient response. So what we did is we had this transfer function and we applied a unit step at Vs, and we wanted to study how the output behaves as a function of time. So let's do the same thing here. So let's assume that Vs of t, the input signal, is a unit step function, and we want to find Vo of t. This is s, but we want to find t. So we have this, and we'll write the so we'll take the inverse Laplace transform of this to find the time domain output voltage for this transfer function. Okay, so I'm instead of writing these big numbers, I have replaced them with a and omega. A is this, omega squared is this. So we can write this as a1 divided by s plus a, s squared plus omega squared 1 by s. And in order to take inverse Laplace transforms, we have to do partial fractions. So we'll take a1 out, and some constants, I'm not worried about the constants here, s plus a, s squared plus omega squared, and s. And you hopefully remember that when you have a quadratic in the denominator of a partial fraction, the numerator has to be a first order polynomial. So this has to be c2s plus c3. Okay, so this is our form, and I hope that you know to find the inverse Laplace transform of each of these. If you don't, you can always find a table of inverse Laplace transforms on the internet. This we've seen before. When you have an s plus a in the denominator, of course, first of all, if you have just s, the inverse Laplace transform of this is just a unit step, which for t greater than 0 is just 1. So the inverse Laplace transform of this is just c4, which is here. Of this is c1 into e raised, so there is a delay, so there is e raised to minus at, where this is a. So the first term is c1 into e raised to minus at. c2s by s squared plus omega squared, the inverse Laplace transform is cos omega t. c3 over s squared plus omega squared, the inverse Laplace transform is a sine omega t. The constant changes. I think it is c3 by omega, but you just check, or c3 into omega, I forget. It's not relevant. The point that is relevant is that the time domain output of this system exhibits a undamped sinusoid. This is going to oscillate even though the input is just a constant voltage applied, which is of course not surprising, because we already know that when that condition of a equal to minus 1 is satisfied, the system oscillates. This is just another way of arriving at the same result. So we've shown mathematically that this particular system, when put in unity gain feedback, will exhibit sinusoidal oscillations. Okay, now so look at this number 123, and as I said, this is 123.21. Now let us increase this gain, the low frequency gain, from 123.21 to 124. Very slight, very small increase. And now let's study the effect of this, first on the Bode plot and on the Laplace transforms and on the step response. So the Bode plot we'll just do qualitatively, of course. And of course I have exaggerated here because This is a very small change, but just so that it's visible, I've exaggerated. So basically what happens to, let's think about it. What happens to a Bode plot when its low frequency gain is increased? All that happens is that the entire magnitude plot shifts upwards. So earlier whatever the gain was, there's a new gain, and everywhere, everything, it just shifts upwards by that quantity, by that change. So that is what happens. Okay. What is the impact of this on the unity gain frequency? So this was the earlier one, that darker is the new one. So the earlier one had the unity gain frequency at this point, 33 times 10 raised to 7. Now, because the whole plot has shifted upwards, the unity gain frequency shifts to the right. The unity gain frequency is higher. Okay, so this is the effect of increasing the gain. The unity gain frequency becomes higher. What happens to the phase plot when you change only the magnitude of a transfer function? The low frequency gain, the constant in the numerator. If we change only that, the phase plot remains unaffected, because a phase plot does not depend on the magnitude of the gain at all. It only depends on the position of the poles, the pole frequencies, so it remains unaffected. Therefore, so what happens? The phase at the unity gain frequency now in the new case, the phase is more negative than minus 180 degrees, because the unity gain frequency has become higher, and as it is higher, the phase is more negative than minus 180 degrees. So again, in terms of phase margin, we say that now the phase margin is less than 0, because the actual phase is, let's say, minus 182 or minus 183 degrees. Phase margin is this plus 180. So 180 minus 183 is minus 3 degrees. So it is less than 0. Okay, now let's do the mathematics. So this, let's go back to that form. So this was the form we had. So either this or this. The low frequency gain is 123. These are only affected by the pole. Only this 123 is the low frequency gain. So we write it in the same form, but instead of 123, we write 124. So this is 124. This is 124. Now again, we find the roots of this cubic. So I did use that website. So it turns out that the first pole location, so again this is 1.11, does not change at all. This pole location does not change. It does not change because the change in gain is very, very small. Okay, if the change is high, of course this will change, but because this is small, this pole location does not change. The complex conjugate poles, so that had an imaginary part, the imaginary part also does not change. It is the same magnitude as earlier. But what has changed is that now a real part is added. So increasing the gain slightly above that the value that was giving us minus 180 degrees phase shift causes a real part to appear in this complex conjugate poles. More importantly, you see this is negative. This pole of the root of this is negative. One says that this pole is in the left half plane of the S. The S is a complex plane, so this is in the left half plane. It's to the left of the 0 axis. This is in the right half plane. It is a positive root. And if you recall, okay, let's finish this. So if I write this as factorized, so this will become S plus this quantity, and then you think about it, you can write this as S minus this whole squared plus this squared. Alright, so just I'm not sure if you agree with this. If you don't, you have to sit and think for 5 minutes and convince yourself that this is the way to write these roots. Okay, so this is the addition. Incidentally, the reason these two are not changing, as I said, it is because the change in the gain is small, and the change in the gain is small makes this quantity. So if you look at this is much smaller than these two quantities. So all these are manifestations of, oh I'm sorry, this is 124. Okay, this is 124. Gosh, okay, change it. 124. Okay. Okay, so now let us see what happens to the inverse transform. So this is the form we can write it in. So s plus a, s minus b plus whole square plus omega squared. So this b is additional in this new with the new gain. And if we do partial fractions, I am writing this in a specific form because this makes it easier to find partial fractions. So c1 by s plus a gives e raised to minus at, c4 by s gives c4. Both these terms have in the denominator s minus b the whole square plus omega squared. Again, this s minus b causes an exponential, just like x plus a causes s minus b, and that appears for both the cos term and the sine term. So this is exponential of bt. So what do we see? What we see is that now, because of this s minus b, we have VO as a function of time, which has a term that rises exponentially with time. It increases exponentially with time. And of course, whenever you have a function that is increasing exponentially with time, theoretically, the function will go to infinity. In a real actual electronic circuit, the voltages, the VO, will get limited by the nonlinearity of the circuit, as we have discussed briefly in, I think, lecture 6 on the feedback. Also recall from that lecture that this happened, the positive exponential happened in our circuit at that time when there was positive feedback in the circuit. In fact, what this implies, this e raised to plus bt implies, is that our circuit, this transfer function, which one? This one. This transfer function, okay, actually, let's go back here. So let's look at this form. So kind of think of this form with 124 here. So a over 1 plus a with 124 here. What all this analysis is telling us is that at some frequency, high enough, let's say above the unity gain frequency, this whole quantity achieves a negative value, and because it is negative, we effectively have positive feedback. And because we have positive feedback, there are exponentially rising terms in the output voltage in the time domain. So this is what happens. If the phase margin is negative, or if when the gain becomes unity, if the phase is less than minus 180 degrees, then the system has positive feedback, the output grows exponentially, and of course therefore it is unstable. Okay, so let's summarize this again. Okay, so what I just said is here, such an amplifier is called unstable. Whenever is an amplifier has a phase margin less than or equal to 0, then amplifier exhibits oscillations, and so it is unstable. By the way, I have not proved this. I have illustrated this with an example. Proof is not easy, so we will not go through the proof. I think you may do the proof of this when you do a course on control systems, control theory. Here we'll just take it by this illustration. We'll accept that if the phase margin is less than 0, the amplifier will oscillate, which means that for a stable amplifier, the phase margin must be greater than 0 degrees. Alright? Okay. Now we'll see later in the next lecture that phase margins close to 0, although they achieve stability, they show a lot of what is called ringing or a lot of underdamped oscillations, and that's not desirable. So for a good stable amplifier, desirable phase margins are greater than 45 degrees. Even better is 60 degrees. Alright, so our goal in life would be to make sure that the amplifiers we have designed have phase margins greater than 45 or 60 degrees. Alright. In fact, for our discussion, we'll assume that we have a phase margin of 45 degrees. So let's think about that for a few minutes. So let's assume that let us say that we want a phase margin of 45 degrees for our amplifier so that it is nicely stable. Now let's think about the implications of having a phase margin of 45 degrees on the Bode plot. Okay. Now a phase margin of 45 degrees implies that the phase shift of the transfer function must be minus 135 degrees, because by definition phase margin is 180 degrees plus the phase of the transfer function. If the phase is minus 135, we'll get a phase margin of 45. So what that means is that our transfer function must be such that its phase at unity gain frequency must be minus 135 degrees. This is what we must have for an amplifier to be stable. Now let us recall from a few minutes ago that one pole causes a phase shift of minus 90 degrees at frequencies much higher than its own frequency. A pole causes a shift of minus 45 degrees at its own frequency. And of course, minus 90 minus 45 is minus 135 degrees. What this means, putting all of this together, is that for a phase margin of 45 degrees, we can afford, have I written it here? Yeah. The Bode plot must have only one pole before the unity gain frequency and the second pole at the unity gain frequency. Right? Only two are possible. One giving this, one giving this. So this is a Bode plot we must get for stability. The Bode plot starts out flat. At the first pole it starts falling, and then at the second pole, okay, let's look at a phase plot first. So at the first pole the phase is minus 45 at frequency is much higher than P1, this is minus 90. Then it turns out that so here the assumption is that P1 and P2 are about 2 decades apart. So P2 starts acting here, and then at P2 the total phase is minus 135 degrees, minus 90 from P1 and minus 45 from P2. And if we want the phase margin to be minus 135 degrees, and P2 must be the unity gain frequency. Alright, so this is required for stability. Okay. Now let's think about high gain amplifiers. Now we already have studied designed a high gain amplifier. We know that high gain amplifiers require multiple stages. At least 2 gain stages they will require. Because one gain stage gives about 200. By high gain I'm talking at least 1000, 5000, 10,000. So you require 2 stages. Each amplifier stage introduces 1 or 2 poles to the transfer function. 1 or 2 because when you cascade stages, which stage gives which, don't know, but 1 or 2. Therefore, high gain amplifiers will always have 3 or more poles. Alright, if I have two stages, I'll at least have 3 poles. I may have 4, but I at least have 3 poles. Also, because they have a high gain, the 2 or 3 poles are likely to be above the unity gain frequency. Alright, because I will just see that in a minute. No, we'll not. We'll see that next time. We'll see next time. Okay. For now, okay, let's go back here. Imagine moving this whole magnitude plot up, or consider the case where the gain is high. See, this gain is not high. That's why the is falling to P2 kind of within 2 decades. Imagine that this whole thing is moved up, way up. When it is moved up, indicating that the amplifier is a high gain, P1, P2, P3 all will be above the unity gain frequency. And that is not acceptable because we can have only 1.5 poles, one here, for stability. Therefore, high gain amplifiers with 2 or 3 poles above the unity gain frequency are almost always unstable. Of course, understood under negative feedback. So this is the state now. We studied stability. We concluded that for an amplifier to be stable, it can have only one pole above the unity gain frequency and the second pole at the unity gain frequency. But if as soon as we design a high gain amplifier with all its poles and its high gain, it is going to be unstable. So this is the problem. So next lecture we'll solve this problem, or we'll study one solution to this problem. Okay.